Yes, we're going to continue our discussion of applying a straightness tolerance to a cylindrical feature of size. Straightness tolerance to a cylindrical feature of size. Um, on a drawing, an orthographic view, you're going to apply the straightness with a diameter symbol, right like here. The RFS indicates the control of the derived median line. That's what we're going to do. So here's our derived median line. And the cylindrical tolerance zone is a diameter of the specified tolerance value. That's our tolerance zone right here. And it does not establish tolerance zone for surface elements. It's only establishing a tolerance zone for the derived median line. That's a little bit different. In the slide we talked about surface elements, applying the form tolerance to the surface elements of a cylinder. This is a little bit different in that now the tolerance is a circular tolerance for the derived median line of the part. Okay. So what this does for us, it's here's how we interpreted the tolerance. Okay, so we have a diameter 1 inch 250 thousandths plus or minus 10 with a straightness tolerance of 7 thousandths diametrical at maximum material condition. What does that mean? Okay, so we have our form here. Our maximum form would be the 267. How do we get to the 267? That is essentially the virtual condition, the MMC of the shaft plus the tolerance. So if we take the 1.250 up to the maximum dimension of 1.260, and then we add to that the 7 thousandths straightness tolerance, we get 1.267 virtual condition. So here's our virtual condition. And then our part has to fit in there at MMC with 7 thousandths positional tolerance here, 7 thousandths form tolerance here. And it applies to the median line, and it's a diametrical shape tolerance zone. Okay, so what does that mean? Okay, well that means when I'm producing my part at its maximum material condition, that's the biggest shaft, I have 7 thousandths tolerance to work with. Okay, but again, this is GD&T and how it has to do with fits. If I produce that part at sizes smaller than the maximum material condition, I actually end up getting more effective allowance on the form tolerance. Okay, so for instance, if I made that part at 259, I no longer have 7 thousandths form tolerance. I got 8 thousandths. Okay, because I still have to fit this virtual condition envelope. Okay, and let's say I made the part all the way down at the minimum size of 1 inch 240 thousandths, I would get a total of 27 thousandths form tolerance. Okay, so really this introduces the whole topic of the bonus tolerance in GD&T. When you're working with MMC modifiers and you're working to assure that your parts are going to fit, as you deviate from maximum material condition, as your part gets smaller, in this case from maximum material condition, I actually pick up more form tolerance. Okay, because what the GD&T does, it assures the fit of your mating parts. Okay, so let's talk about material condition modifiers for straightness now. The MMC modifier indicates specified tolerance values applies when feature is at its MMC size. Well, in that case, you're going to get additional tolerance if it departs from MMC. Okay, an LMC modifier indicates the specified tolerance value applies when a feature is at the LMC size, and then additional tolerance is permitted if the feature departs from LMC. And I'm going to tell you right now, after working in the industry for a long time, we use MMC a lot more than LMC. MMC, you're looking for fits, you're looking for how parts fit together. In LMC, it's not as useful. There's certain things it can do for you really well, like guarantee a edge distance, for instance, on a feature, on like a hole with respect to the edge of a part. But for the most part, you're going to be using MMC modifiers primarily. Okay, let's talk about the virtual condition. The virtual condition boundary is created when the tolerance with MMC or the LMC modifier is applied to an external feature of size, such as a shaft. That's the virtual condition. So the straightness is applied at MMC on a cylindrical shaft. The virtual condition is the shaft size plus the straightness tolerance, like we did in the example right here. Shaft size plus the straightness tolerance. Additional tolerance is permitted when the size departs from MMC. That's the bonus tolerance. And the straightness applied at MMC on external diameter, the virtual condition is the shaft size minus the straightness tolerance, and then additional tolerance is permitted when feature size departs from LMC. So yeah, we're going to actually call it bonus tolerance now. Additional tolerance, allowable straightness tolerance, results from the departure of MMC and LMC. So the allowable tolerance is specified tolerance zone plus the additional tolerance. Okay, there's our virtual condition. The additional tolerance is in the size departure from the specified material condition. Okay, so what happens here is you actually pick up some bonus tolerances. Like I'm saying, as you're down by 1 inch 240, you get 27 thousandths. Okay, so that's one of the beauties of GD&T is you're assuring that your parts fit. You're ensuring that your parts fit, and you actually get up more tolerance as you get away from the maximum material condition, which will be where you start to lose the fit on the parts. So let's talk the straightness of a derived median line of a hole. Okay, so in this case, it's very similar. How do you apply it? On a model, you go into the annotation plane, and then you apply the form tolerance, the straightness tolerance, right to the dimension. Okay, kind of like what we did with cylinders. Or you can do it this way, where you can apply it to the dimension line, or you can apply it underneath here. These would be the ways to apply it in an orthographic view to a hole. So what the virtual condition of a hole means. The virtual condition boundary is created when the tolerance with MMC or LMC is applied to an internal feature such as a hole. The straightness applied MMC on an internal cylinder, so you get a virtual condition, and that's going to be the whole MMC minus the straightness tolerance. And then again, the bonus tolerance, additional tolerance, will be permitted when the feature size departs from MMC. So let's talk about the MMC there. Okay, how do you interpret this tolerance? So I've got a diameter 750 thousandths plus or minus 6 with a straightness tolerance of 5 thousandths diametrical at MMC. What does that mean? So first of all, we have to find the virtual condition of the hole, which is the MMC size, which is 750 minus 6 thousandths, and subtract from that our form tolerance. And we have a virtual condition of 739. Okay, that's shown here. Here's our virtual condition of 739. And then our tolerance zone is a diameter shaped, a round shaped zone of 5 thousandths, tolerance at MMC. And so that's what we got. So we produce this thing at MMC, which is 774, we get 5 thousandths. But as we deviate from MMC and that hole gets larger, we get, for every thousandths we deviate from MMC, we pick up another thousandths in allowable form tolerance. Okay, so when we're down here at our maximum, our minimum material condition, which would be the largest hole, we get 17 thousandths allowable tolerance. That means at the least material condition here, we're going to have the most allowable variation and still be able to get our parts together. That's what that means. Okay, I'm going to briefly talk about how to verify this. Really what you do is for a functional gauge of a shaft dimension like this, what you really do is make a gauge here that has the virtual condition of the part with the tolerance. And then if I was able to pass my production part through that hole, made it the virtual condition, my part is good. For checking a hole, for instance, we have this tolerance right here. Okay, we have a size tolerance with the straightness tolerance. We would calculate the virtual condition. In this case, would be 1 inch minus 10 thousandths, which is 990 thousandths. And we would subtract from that our form tolerance here, and we get 985 thousandths. Okay, so our gauge is simply a pin here made at perfect form at 985 thousandths, and as long as it slipped through our hole, we would be good. I'm going to end this movie right here, and the next one we'll start talking about flatness tolerances.